Welcome to Z-Tech Amateur. Today we'll be building a capacitor ESR tester which measures the equivalent series resistance of capacitors. Ideally, you want this resistance to be 0 or as low as possible, which means that you have a very high quality capacitor if this resistance is low. We'll actually build two circuits. One is a qualitative tester, the other one is a quantitative tester. It's going to be a little bit more involved than the previous video where I showed you how to build a leakage tester, where the circuit was actually pretty simple. So here we actually have to build an oscillator, and we'll go through and go through the building of the oscillator. We'll build a Wien bridge oscillator, which is really interesting, and we build a tester out of that. So it's going to be a fun project, and let's get started. So here's a little introduction of how we're going to measure ESR. In this diagram here, the way we're going to attempt to measure ESR, right, is that we're going to have a signal source, and that signal source has an internal resistance that is, we can try to get as close to 0 as possible. But of course, every signal source is going to have some internal resistance, and it will depend on that, how accurately and how well we're going to be able to measure the equivalent series resistance of the capacitor. So the idea is that we have a sinusoidal signal source, and then we connect the capacitor to it, and we measure the voltage drop or voltage across the capacitor. What we want to figure out is what is this sort of internal resistance of the capacitor which is in series with the capacitor. This typically is very low, a couple of ohms, although with older capacitors and bad capacitors it can be quite high, into tens of ohms or even higher. So looking down here at the signal source, we have the internal resistance, and then we have the ESR, and we have the actual capacitor. So this portion here is the all inside the capacitor, and so we just put a probe here and to ground, and we're going to measure what is our AC voltage. And this has to be AC, and the reason it has to be AC and it has to be sinusoidal is that we want to make this frequency high enough where the capacitance reactance is close to 0, or it's as close to 0 as possible so it doesn't affect the ESR measurement. So typically this frequency, depending on what size capacitors you have, could be 10 kilohertz or even 100 kilohertz. So as we will see later on, we'll build this oscillator. It has to be a really nice sine wave generating oscillator with also a pretty low or really low output resistance or output impedance, and that's going to be our signal generator. However, first, before we do that, let's talk about the qualitative measurement of a ESR. So the qualitative measurement ESR is similar to this, but instead of the signal source, we have an audio amplifier, which also has a pretty low internal resistance. We put the capacitor to the output of the audio amplifier. However, we also hook up the speaker. So basically think of this as we just hook up the capacitor in series with the speaker of the audio amplifier. So what happens here is that the capacitor's ESR, if it's too high, could be the dominating resistance of the audio circuit. The internal resistance of the amplifier is usually pretty low, close to 0 ohms. The speaker itself is maybe 4 ohms. And if the capacitor's resistance, or ESR, is up in the tens of ohms, for example, then it's going to cause a distortion, a very quiet sound. And so that's one way to qualitatively measure the ESR of a capacitor. With this qualitative measurements, you kind of have to have a ground truth, known good capacitor, roughly about the same capacitance as what you're measuring, so you kind of know what sound you're looking for. Because if you don't know, then it's hard to tell if it's ESR or just the capacitance is low. So what I've done here is that I've selected a couple of capacitors. One of them is a 3.3 microfarad film capacitor. We'll see how this sounds. This one is a 68 microfarad electrolytic. We'll test it out. This one is a 2.2 microfarad electrolytic. I'll solder some leads on it because the leads were really short. And this one is a 1 microfarad electrolytic. Actually, this is from a Soviet little radio that I took out. So we'll test these capacitors with the audio amplifier, and we'll see how they sound. Here I zoomed out just to show you the hookup that I have for a qualitative tester. So I have an audio signal coming in on a 3.5mm jack here. This is a little audio amplifier. It's a Class D amplifier, which has a very low output resistance or impedance. The amplifier is hooked up through the 68 microfarad capacitor to the speaker. The speaker's over there. And then I have just the power coming from a bench power supply, about 12 volts. And we'll see how this is going to sound. Okay, let's listen to the sound of the 68 microfarad capacitor. Now this is a good capacitor. I know has a good ESR, as in a low ESR. But let's listen to the sound here.
Quand j'arrivais, elle sortait du café. On s'est dit bonjour très vite. Elle était gaie, rayonnante et pressée.
Okay, so as you can hear, the sound is clear. It has, pretty good bass. That's because the capacitance is 68 microfarads. So we're not looking to see how bassy the sound is. We're looking to see how clear it is or clean it is, and how loud it is. All right. So the loudness is going to be one of those factors. Is there a lot of resistance in between the amplifier and the speaker? You're going to hear a much quieter sound. Okay, next we're going to look at the 3.3 microfarad capacitor. So leaving the volume the same as it was before, here's how it sounds with the 3.3 microfarad capacitor.
Comme avant que l'on se quitte, elle n'a pas eu même un peu d'émotion. Ce n'était qu'une passante, lointaine et indifférente, désormais. Oh Mélisa, si encore tu pouvais pleurer. Oh Mélisa.
So you can hear that obviously there's a lot less bass and a lot less volume because of that. But, we still hear some sound, and the sound is fairly clean. And qualitatively speaking, for a 3.3 microfarad capacitor, this is pretty good, right? It doesn't indicate that it has a unusually high ESR. So, this is expected, right? We're feeding a 4-ohm speaker through a 3.3 microfarad capacitor, so it's expected to kind of have this light sounding sound in this case. So now we're going to take a closer look at even smaller capacitor, which is the small thing. I zoomed in a little bit. It's a 2.2 microfarad electrolytic. Now clearly it's much smaller than a 3.3 film capacitor, because the film capacitor was rated 600 volts, and so this is, I think, 50 volts or something like that. But we should hear similar sound to the 3.3 microfarad electrolytic. So let's see if that's the case.
J'en aurai moins de chagrin.
So you can hear that it is similar to the 3.3. I would consider this also to have a pretty good ESR. It doesn't really affect the sound all that negatively, especially when we compare it to a known good, 3.3 microfarad versus 2.2 microfarad. Okay, on to the next capacitor. So here we have a capacitor that is a 1 microfarad capacitor, 50 volts. It came out of a little portable Soviet era radio, so-called 403. And I know it was bad because the radio was very, very quiet, and replacing this capacitor fixed the problem. So what does that tell us? That tells us that this is probably going to be having a high ESR, as in it's just attenuating the sound quite a bit. So here we go. Nothing. You can hear nothing. I have the music going. I have the amplifier at the same volume. Absolutely nothing. Now let me try to increase the volume a bit just to see. Not even there. I have to go on the computer and see if that does it. Yeah, absolutely nothing coming through this capacitor. So that tells us that the ESR of this capacitor is very high. So we'll use this capacitor as the guinea pig for when we're going to build our precise ESR measurement tester, knowing that this is going to be one of those capacitors that's going to read very badly. Okay, so there's your qualitative tests of good versus bad capacitors. Clearly this one microfarad capacitor was a bad one. I don't have a bigger size capacitor that I know has a low ESR, but the sound difference will be astonishing if you find something that has low ESR at even at higher microfarads. The bass will be there, but just the volume of the sound will be much, much lower than with a good ESR capacitor. And that's one way you can test as well, is you can just set the volume of the amplifier and output source to a certain value and just get a whole bunch of capacitors that are all, let's say, 100 microfarads each, and then just go through them. Whichever is the loudest by ear is going to have the best or the lowest ESR. So that's one way to really select the best capacitors as well, right? You don't need to have precise measurement. You can just listen to the sound and see which one has the sort of the loudest, cleanest, clearest output. So now let's talk about the actual precise measurements of ESR. So going back to what we want to build here is that we're going to build a signal generator, a sinusoidal signal generator with a low internal output impedance, low RS here, close to 0 ohms. Of course, before we do anything, once we built it, we're going to have to measure this. So we're going to build this circuit, then we're going to measure this output impedance, so we know exactly what this is. And with the signal generator, you have to adjust it to a certain frequency and then measure that output impedance. It might change with frequency. So we'll pick a frequency that is going to yield us maybe by 0.1 or less, ohms of capacitor reactance at that frequency. So, for example, if you're only measuring 1,000 microfarads and up, then the frequency probably could be, 1 kilohertz or so. But, if you want to measure all the way down to, let's say, 1 microfarad, then we probably have to go above 100 kilohertz to really get that low reactance of the capacitor. And just as a reminder, reactant is quote-unquote the resistance at frequency of the capacitor. So the higher the frequency, the lower that reactance is. And that just basically means the capacitor acts more like a short at that frequency. So we want the ideal capacitor, the actual capacitance, to be basically a short, so we can actually start measuring the ESR, which won't be a short, or we hope that's a short, but reality will tell us that it won't be a short. And the way we're going to measure it is, just basically looking at down here. Let's pull this up a bit. Looking at down here is we build the oscillator, measure the internal resistance, put a capacitor at test. Remember, the capacitor is represented by ESR and the ideal capacitance. Now, of course, I left out the EPR, which is the leakage capacitance, and all kinds of inductances. So just for simplicity, we'll assume the capacitor is just ESR and a capacitance. And we'll put our AC voltmeter here, right here to this terminal, and we'll measure the voltage. And so from that voltage of drop of the capacitance, we can actually calculate out ESR. We know what RS is, we know what the frequency is, we know what the reactance is of the capacitor at that frequency. So we're able to know exactly what that is. So if this is 0.1 ohms, we'll put 0.1 ohms here. We put, let's say this is a half an ohm, we put a half an ohm there. We know what the voltage is there, and from that we can actually use a little bit of math to calculate ESR, and I'll show you how that's done once we get there. Oh, and one more thing, from a previous experiment with the qualitative measurement, on that little amplifier, I hooked up the capacitor, the output capacitor, such that the positive lead was always at the, sort of the red wire here. And that's because this little amplifier just powered with plus 12 volts. It's a single-ended power supply, so it doesn't have a doesn't have a very good, doesn't have a center power supply, so it doesn't have a plus 12, minus 12 power supply, which will make it balanced. So that means that if between ground and the positive wire output for the speaker, there's likely going to be more of a positive voltage. And so for safety, for electrolytics, hook up the positive side to the red wire, negative side to the speaker, and then the other side of the speaker goes to the black wire. So that's just a little tidbit. Otherwise, you can blow up the capacitor, especially if you crank this up. This little thing can do like 30 watts or 50 watts or something. Even though it looks small, it can easily blow up an electrolytic that's hooked up backwards. All right, let's look at the schematic. So a little history here with this schematic. While I kind of take this in a little bit, I'll let you look at it for a second. There's a little known company back in 1939 or 1938 called Hewlett-Packard that got into the electronics equipment business. They made instruments with the very first product, which was a very low distortion sine wave oscillator. Of course, it used vacuum tubes back then, but they came up with this idea of using a Wien bridge, which hasn't been invented in the 1800s sometime, the bridge itself, but the electronic circuit, of course, has been invented actually by Hewlett-Packard. And specifically, the part of this little light bulb here was the trick to this oscillator. And you might think, well, there's all kinds of ways we can do it today with feedback and diodes and circuits and things like that. That light bulb is the trick to this whole oscillator being low distortion. In fact, you can get really, really low sine wave distortion, 0.0001% distortion, with the velvet circuit. Now, I don't know if this one's going to give us that, but we're going to try. Having a low distortion sine wave is critical for ESR measurements so that our AC voltmeter is not going to measure a bogus reading. So if we're reading a square wave or some other wave, it will likely measure a bogus reading, and we won't get a nice, accurate ESR measurement. So anyway, back in 1939, Hewlett-Packard released the very first product, which was a sine wave oscillator using this light bulb. Not this one, but similar. And it had a very, very low distortion output. And, that's the test equipment or bench equipment that got them started as a business, and they did a whole lot more things since then, but this was their thing. And so we're going to rebuild this circuit. It's a very low distortion Wien bridge oscillator. And, this circuit is analog, so it's going to become a little bit of tuning. So I'm going to start with a breadboard design, and then we're going to build it on a protoboard. I'm not going to build a PCB, I usually don't. The protoboards are very, very sturdy. You can solder, on the components on there, and they'll never come off. They're as good, if not better, than a PCB. So we're going to build the final circuit on a prototype board. Alright, let's go through the circuit a little bit. And this is looks simple, but it's actually very complex. But, I'll try to explain it as best as I can. So first things first, the Wien bridge is a capacitor resistor bridge with a series capacitor and resistor here and a parallel capacitor and resistor there. They both have to match. The capacitors have to match and the resistors have to match. And especially when you have a variable resistor like I have here to set the frequency, they have to match. Now, if they don't match, it will still work, but the quality of the sine wave suffers. And so Hewlett-Packard back in the day, obviously manually matched the capacitances and the resistors, right? And having this little 100 ohm here in series allows you to kind of match this a little better. So I might change this out to like a 98 ohm or 91 ohm or 95 ohm resistor, made up of a bunch of resistors to try to get this as close as possible. And the frequency is given by 1 over 2 pi times RC, and R is, in this case, would be whatever the variable resistance is set at. Let's say it's 100 kilo ohms, so plus 100 ohms, so 100.1 kilo ohms, and then the C is 2.2 nanofarads. Okay, so back to the circuit here. So we have this Wien bridge that works on the principle of positive feedback. All oscillators kind of work on the same principle. So it's connected to the base of this transistor, which then amplifies, like these two transistors continue amplifying, and then we have a low impedance positive feedback coming back here. It's coming off the emitter of this transistor, meaning that this is going to be a very low impedance feedback point. And that's important because this amplifier, we want to seek 1x unity amplification, or very, very close to it. And that's when you get the best oscillation and the best sine wave out of it. So here the signal comes in, gets amplified. We have a positive feedback loop here, and that creates oscillation. To make sure oscillation actually happens, because this circuit will not just work, we have this little trimmer here to make it oscillate. So we'll just have to adjust this little trimmer to get it to oscillate. So that's one trickery that has to be in there, because you can't calculate this out to the precision that you want, because the betas of these transistors vary, and if you get into higher frequencies, there's all kinds of other ill effects that happen in the circuit. So we're not gonna try to estimate this resistor and remove that variable trimmer. That's just going to be there. And then the frequency range here roughly is going to be somewhere in the hundreds of hertz, probably around like a couple hundred hertz to almost 1 megahertz. If I crank this potentiometer all the way to a short, it's going to be just this 100 ohm resistor, as part of the Wien bridge. So that's going to be almost 1 megahertz, which you probably don't have to go that high. But if you want to measure the ESR of a very low capacitor, like a 0.1 microfarad capacitor for whatever reason, then we'll have to crank the frequency up that high. Likely it won't oscillate across the band here. We'll have to adjust this to oscillate in a certain frequency range, but we'll figure that one out. Now, what about the light bulb? So the light bulb is actually the trick to this oscillator. Its role is to provide a stabilization point for the emitter of this transistor, meaning that the light bulb is a variable resistor based on the amount of current that it goes through. So when there's more current that goes through the resistor, this will have a higher resistance. It might be lower, and I always confuse those two things. But anyway, it will be, the resistance changes based on the amount of current that goes through a light bulb. And it changes such a way that this amplifier, when it's trying to amplify a lot, like more, where its amplification goes above 1, this light bulb will bring back the amplification close to 1 or near 1. And by 1 I mean 1x amplification, so that the voltage going in here, it's the same as the voltage going out there. So that's the trick with that. So that basically keeps the whole circuit in balance and close to the 1x amplification factor. And that's the trick that Hewlett-Packard came up with back in the day. And even today, I see all kinds of circuits that try to use diodes and a whole bunch of other FETs and things like that. Not as good as a light bulb. So we're going to actually use a light bulb today and build a circuit. In fact, I have a couple of different light bulbs, and we'll try them out and see which one works the best. And we'll kind of tune that a little bit. And finally, the lower leg of the Wien bridge connects to this point here. And this is This is practically ground. You know, it's bypassed by a 100 microfarad capacitor, which is AC wise, it's ground. Now, to reduce the output impedance even lower than this is, which is fairly low, I've added a little extra stage here, which is an emitter follower, and this has like a 100 ohm resistor here, and I calculated these values out. We'll see if they hold, so that the output impedance here is, you know, close to 1 ohm or thereabouts. And again, we'll measure that when it's time to do that, because we do need to. That's that RS on the diagram, that, you know, that output impedance. And then finally, the whole thing is powered from a 9-volt source. You know, it could be a 9-volt battery, so I tuned these resistances, at least initially, to work off a 9-volt power source. But obviously, we can you know, power it off a 12-volt bench supply as well. But some of the resistances might have to be tweaked or changed for that. Okay, next step is we're going to build this on a breadboard. So here's the Wien bridge oscillator on a breadboard here. And let me just explain what I've done. So I've used the variable potentiometer here, which is a 2-ganged potentiometer. If you remember from the schematic, we have the Wien bridge resistor capacitor network, and it requires 2 resistors to be the same. So this is the ganged potentiometer there. I have the 2 resonating capacitors, these white film caps here. They're 2.2 nanofarads. I have the little light bulb right there. It's a 75 milliamp 6.3 volt light bulb. And you know, I have the bypass capacitors. They're 100 microfarads each, and I have a big final stage capacitor. I think it's 2200 microfarads. The transistors are 2 and 3904s. You know, you can use anything really. It doesn't matter. The 2 final stage transistors could be a little bigger, but you know, for this purpose, I'm not going to run this 24/7. So, you know, these are pretty good. Typically, I would use a 2N2222. You know, for the final stage transistors, they can handle quite a bit more current and are, you know, fairly good for RF. So, as I said, this, you know, this will go into, I guess, low range RF into maybe up to a megahertz. So anyway, everything is hooked up. I turned this on a little bit before, and this resistor got a little hot, so I upped it to 220 ohms. If you remember on the schematic, this was 100 ohms. So that's the only thing I changed so far. So let's see how it works, and I'm gonna zoom in on the oscilloscope here and see what we get. So here's the scope. As you can see, we don't quite have a sine wave here. We're at 41 kilohertz, but it's definitely not a sine wave. So I'm just going to tweak that trimmer resistor, not the frequency adjustment, but the other resistor, to try to fix this up. It's going in the wrong direction here. It's getting there, but it's just not quite. It's not quite making it. We just have a bottom half of a sine wave there, and then the oscillation goes away. So, you know, the analog circuitry here is you know, getting in our way to get this working. So, you know, there's differences in the betas of the transistors, resistors, and, you know, with analog circuits, you gotta breadboard it to figure out, you know, what's going on. I'm gonna increase the voltage because I know some of these circuits like higher voltages, so I'm gonna just set the voltage a little higher. Just do like we'll do 12 volts here. So 12 volts. Let's see if I can get any better results here. Okay, let's see. It's a little better. Almost, you can see it there, and we can actually get a sine wave going. So maybe I'll increase the voltage just a little more. go all the way up to 16. The oscillations have gone away. So let's bring those back. And there it is. So here you can see that I'm doing okay. It's pretty good. There's a little bit of flat topping there on the sine wave, but it's looking pretty nicer. So what I will have to do is I will have to maybe tweak the resistors a little bit just to make the circuit work at a higher voltage, because right now the resistors are kind of set for a lower voltage, and so it sounds like we want to be a little higher voltage. And also, this also has to do with the light bulb as well. So the light bulb 75 milliamps is a little high current, so maybe the higher voltage will work better. Actually, the light bulb's a little lit, so I'm going to show you right here how that looks on the circuit board. So here's a circuit with 16 volts applied. I don't know if you can see it, but there's a little bit of filament, a little bit of light, light coming out of the light bulb, which means that our current is just a little too high. We don't want that light bulb to be even visible, because the light bulb, as I said before, we want it to act as a variable resistor based on the amount of current that goes through it. And so when the filament is lit, it starts losing that property. So we kind of want to reduce the current a little bit on there. So let me show you the schematic here with some tweaked resistors, and we'll change that out and try it again. Okay, trying to get the schematic to show correctly here. So here's the schematic we just went through and built. And so I went back to the drawing board a little bit and kind of thought about, looked at some reference schematics, thought about like how much current I want going through here when I increase the voltage to 16 volts. So the first thing I've done is I changed this emitter resistor here from, 220 to 680 ohms. And that's going to reduce the current in the lamp a little bit so we don't see that filament, which is important. To have that, just a nicer, better effect of a current-driven resistor for this lamp. Then I changed this resistor, and that's basically just to account for a higher voltage, just less current through this transistor. We don't need that much high current here, so just tweaked it up a little bit. And then the final sort of transistor in the loop itself, I changed this resistor from 220 ohms to 330. Again, higher voltage. I don't want to burn this one out, and plus we don't need a crazy amount of current here either. Going to the final stage, which is the emitter follower for the super low, ultra low output resistance. I've calculated this out again, so there's online calculators for this one. It's an easy one. It's hard to calculate the rest of it out. You just have to try and see. And you can measure voltages to make sure that the currents are as expected. I calculated this out, and for 16 volts, and with 220 ohm emitter resistor, we should be basically at 0 output impedance. So that should be really good. Hopefully it won't heat up, otherwise I have to bump it up to maybe 330 or something. We'll see. And yeah, so that's the new schematic we'll try out and see if it works a little better, a little more stable. The previous one, I'm a little worried that it's just too finicky for it to oscillate just when you set this trimmer just right. And so we don't want to be in that state, because then you have to always mess with it to get it to oscillate and get your sine wave. As I said, some of that is due to the fact that we want a unity gain for this 3 transistor amplifier stage, or as close to it, to really get that nice sine wave. So basically this just becomes a current amplifier. So we have a high impedance input here, and we have several stages here. We have a low impedance output, but the actual voltage gain should be 1 or close to it, and we can adjust that with this trimmer. Okay, here we go with the second revision. So after a little bit of testing and changing resistors, I made a couple of changes, nothing major. What I've done is I've changed some of the early amplification stage resistors just to tune the oscillator, and for 16 volts, and to kind of watch out for the lamp so it doesn't glow as much or much at all. So just getting to that range where it works the best. I've added a small 2.2 nano capacitor here to the emitter circuit of the second transistor. I'll show you the diagram in a second, the schematic in a second. And that really just helps with higher frequency oscillations, which I want to do. I want to set this to about 100 kilohertz, figuring that that's going to get us the best range to be able to measure low and high valued capacitors. The rest of the circuit pretty much stays the same. I did change this. Originally it was 220 ohm emitter follow resistor. It was getting a little warm, so I upped it to 330 ohms. So now it's actually pretty nice. It's not there's not much heat there or any at all. So let's look at the scope and see how the waveform looks now. Here's the scope and here's the waveform. As you can see, it's looking very nice. So after tweaking the resistors a little bit, I got the transistors in their linear operating region a little better, and that really helps the waveform. And of course, tuning that trimmer capacitor, sets that waveform pretty nicely. So here's an example where if I just start tuning the capacitor, it's fairly sensitive, but it's not overly so where you cannot tune it. But I can make the oscillation stop. But then if I really change it around, the waveform does get a little choppy, but not too bad, nowhere near as bad as it was before. And so I kind of find a little sweet spot there. And that's actually a very nice sine wave. I can just tell visually that the distortion is very low. The peak to peak is about 2.26 volts, as you can see there. I'm not sure how well the screen will show up, but so I'm just going to go through the measures here. RMS is 802 or so, 800 millivolts. And right now the frequency is about probably a couple of, it actually doesn't matter, but it's just 60 kilohertz, 61 kilohertz. We'll set this, when I build this out on a PCB, well, not a PCB but a prototype board, I'll just fix the frequency to about 100 kilohertz or close to, so that I don't have to mess with adjusting the pot there. So yeah, so it's looking actually pretty nice. Okay, so here's the hopefully final and revamped schematic. Just the changes here. In the Wien circuit, I basically simplified things. Just put a 680 ohm resistor here, left at 2.2 nanofarads, and that yields about 106 kilohertz. Close enough. And the frequency doesn't have to be super exact, and I'll tell you why in a sec here. These stages look pretty similar. I played with this resistor a little bit just to get the light bulb not to light up too much, so I ended up having to reduce it just to get some lesser amount of current through that light bulb. I've played with this one a little bit to reduce that as well to get a nicer sine wave. And then as I said, I added this 2.2 nanofarad capacitor here in parallel with this resistor. And all this does, it just improves the amplification of this transistor at higher frequencies. And so, I consider 100 kilohertz higher. It's not that high, but if you were running this at a couple megahertz, then this will help even more. And then the rest stay the same here. I tweaked this one a little bit. 330 I think was the original or the second iteration of resistor here. I increased this one just a tad, again because it was getting a little warm. So my measure of sort of wattage here. These are 1 watt resistors anyway, but I don't want them to get warm, so I'll just tweaked it up a little bit. And then the final stage, which is the emitter follower, the bias resistors change a little bit because I'm trying to get about half the supply voltage. So on the emitter I want about 8 volts and the supply is 16. And so, I calculated these out, but the calculations never really get you the right number. So I play with these a little bit, and then I put the 330 ohm here, as I said, because the 220 was getting a little hot. And then finally, we have a 2200 microfarad output capacitor. And you know, this one is just because the output impedance is going to be pretty low. So I even at like 100 kilohertz, I do want the, you know, really low reactance here, right? So I want a dead short basically at 100 kilohertz. Yeah, what else? I put like a small little 1 microfarad ceramic filter capacitor, really just to protect extra oscillations through wires going through, you know, like it's just with oscillators, you know, you kind of want to kind of drive some of those oscillations to ground, filter those out so they don't go back to the power supply and radiate through wires and all that kind of stuff. So yeah, so that's the circuit. Now, next step, I'm gonna actually build this on this board here. I'm gonna cut it up a little bit, and so this is the prototype board. As I said, I'm not a big fan of PCBs. It just takes a lot of money, time, and waiting. Well, you either pay a lot of money. If you don't wait, then you get a PCB order soon, or you don't pay a lot of money and you wait a month for them. So I don't like either option, and you know, the homebrew PCB is also a lot of hassle. So these are so great. You know, they have solder, you know, have vias across, and you can really solder components on there very solid. In fact, it holds better than a PCB in my opinion. And there's no drawback, right? You have to maybe do a little bit of wiring on the back just to connect things, but other than that, I think this is perfect for projects like these. So let's go on to the math here a little bit. So here's a couple of formulas. So starting from the left side here. Once we build a final circuit, I'm going to measure the source resistance, or also we call this the output impedance of this oscillator. We'll denote that as RS here. And the way I'm going to measure that is put maybe a 10 ohm resistor to the output, and then measure the output voltage with and without it, right? And then we can calculate out RS. Then we're going to also measure the source voltage, and this is RMS. And that's basically just with the scope or meter, we're just going to measure that on the output, straight on the output. And then the formula for calculating the ESR is basically just the resistor divider. So remember, the internal resistance of this oscillator is RS, and then we have the resistance of, quote-unquote resistance of the capacitor under test. And we have the reactance as well, which is the resistance at that frequency, but we're getting that really low because we're running this at 100 kilohertz. So for now, let's ignore that for a second. And so the resistor divider formula is that, you know, if you have an ESR resistor that you're measuring your voltage across here, that's that resistor divided by the sum of the resistors. So the sum of the resistors is RS plus ESR, and then times the source voltage, and then that equals the VM, which is the measured voltage. You kind of shuffle this equation around a bit, and then what you get is the ESR resistance is the source resistance, which we'll measure, the source voltage, which we'll also measure, the measured voltage. So this is when we connect the capacitor to the output, we measure the voltage. All these in RMS, so VS and VM are RMS volts. And then minus 1. So this is pretty easy to calculate, you know, plug it in Excel or things like that. You know, I wouldn't try to do this every single time. And then the next thing is the reactance of the capacitance, which is this formula here, denoted by XC. That's the reactance, and that's basically the resistance to the capacitor at a certain frequency. And we discussed before that the frequency of this oscillator is given by 1 over 2 pi RC, and that with these components, we'll see what the real frequency will be, but with these components, that works out to be 106.4 kilohertz. So we should be around there. On the other side here, I just made a quick table of when we should think about reactance and when we shouldn't. So the true ESR is going to be equal to whatever we measure, you know, on the previous page, or whatever measure and calculate, minus the reactance of the capacitor. Because that reactance is basically, think of this as another series resistor in series with the ESR. So we kind of want to subtract that out of there if if it's a high value. So at this frequency, 106.4, some common capacitors that we need to maybe worry about reactance is if you're measuring a 1 microfarad capacitor, that's going to be 1.5 ohms. So you definitely want to subtract that out in that case. At 10 microfarads is 0.15. Probably recommended to start subtracting that out. But as you go up above that, especially 22, 33, 47, 100, the reactance at this frequency gets just so low that that's going to be within the error of measurement of the ESR. So I would not even bother subtracting that from whatever your ESR calculation is. So yeah, so that's how I wanted the frequency to be high enough for me to kind of be comfortable, like 10 microfarads and up, and even below, but not too high where the frequency is so high that some of the internal inductances of the capacitor play a role. And in that case, if you're running this at 10 megahertz, in theory that's a very, very low reactance, but in practice there is an inductance in the capacitor. So now you're measuring the inductance effects of that, which actually increases resistance. So I wanted to find that sort of happy balance, and so that's how I came up with 100 kilohertz. And magically, here's the board with everything assembled on it. So as I said before, I used this prototype board. I really like these because avoids the whole PCB creation process and waiting on in the mail for it to arrive. Plus, if you made a mistake, it's just easier to fix it on this kind of board. And of course, all the holes have vias in them, so I kind of like that too because it actually has a more solid hold. So when you solder something on here, it really holds it in place. So so in my mind, for prototyping and even for like one-off projects, these green little prototype boards are way better than the PCB, especially if you consider mistakes and waiting and redoing and all that kind of stuff. Anyway, you see the light bulb is there, and I removed the big potentiometer to set the frequency. So I put in two 680 ohms resistors as I've shown in schematic to set the frequency to about 100 or so kilohertz. So we'll measure everything now. We'll measure first the voltages and most importantly the output impedance of this oscillator, which should be very low. And so we'll look at the scope here in a sec and see if it works and see how good it looks. Okay, so you can see here, this is the output of the oscillator, which is unloaded. So I just basically connected the scope and adjusted the variable resistor to get a nice sine wave. It's about 670 millivolts. And what we want to look for here is what is the loaded voltage so that we can calculate the output impedance. So I have a 33 ohm resistor. I'm going to connect that in, basically short the output with that. And I chose 33 because lower values started clipping the waveform. So 33's looks like a good sort of minimum value in the sense that we can measure this fairly accurately. So we're looking at maybe 670 millivolts here. So here's now the resistor shorted to the output. So the waveform's still looking good, and we're down to about 570-ish or so, 569 maybe millivolts. So that's the ratio that we're looking for to calculate the output impedance. Alright, let's look at the math. Okay, let me explain how we're going to figure out the output impedance, or I call it the RS of the oscillator. So here, let's look at this lower diagram here. We have the oscillator, we have RS, and we measured on the scope 670 millivolts. In this upper diagram, I connected the 33 ohm, actually it's 32.5, measured on the DMM, the resistance in parallel, and I measured on the scope 569 milliohms. So you can see here that this forms a resistive divider where I have an input voltage of 670 milliohms because this resistance here is pretty much infinity. It's around 10 megohms, but we can think of it as infinite resistance. So that's the input to the resistive divider. We have an unknown RS, And then the voltage across this bottom resistor, which is 32.5 ohms, is 569. So if you flip this over, up here I just wrote down the resistive divider formula, which is input voltage 670, and then we're measuring across the 32.5 and dividing by the sum of both resistances, which is RS plus 32.5, and that has to equal to 569 millivolts. So plugging it all in, we got RS being 5.7689 ohms, which is actually pretty good. I was aiming for that low output impedance, or RS, of the oscillator. However, I found out after some testing is that we can't really short the output to ground, or put a low resistance there, because the waveform starts clipping. So, you know, its amplifier, or the final stage of the oscillator, doesn't have all that much power to be able to source the same voltage across a short, even though the output impedance is actually pretty low. So what I'm going to do is I'm going to just set this, or connect this 32.5 ohm resistance in parallel with the output, and then I'm going to connect the capacitor under test to that. So that way, even if the ESR of the capacitor is 0, effectively basically having a short to the ground here, we're still going to get a valid waveform, or a good waveform, because we just effectively have 32.5 ohms connected to the ground, just like we had before, and you saw on the scope that the waveform was fine. So we're going to use this total RST I call it, which ends up being 38 plus some 0.2689 ohms, and that's just the sum of the actual internal resistance of amplifier plus the 32.5 ohm. There's one more thing we need to do, which is to measure the exact frequency, or exact as possible. Unfortunately, the scope doesn't do a good job of measuring the frequency. It gives us a ballpark number, but I built this frequency counter fairly recently. It's actually based on somewhat simple circuit, analog front end divider, and it goes into a AVR microcontroller, and so all written in C, the AVR code itself. But yeah, it goes up to 100 megahertz, and I have it set now at the hertz setting here, and it's reading 112 740 or so. It's been the frequency has been moving down as the oscillator kind of warms up. I left it on for about 5-10 minutes now. Started about 112 900 and worked its way down to 700, and so I'll probably use this sort of 112.7 kilohertz number. It's about 10 minutes in. That's fairly accurate, right? I guess if you run it for longer than that, it might be lower, but it's slowing down a bit, so that's good. Anyway, this frequency counter, it's really neat. I actually got a GPS receiver and set that to 500 kilohertz, which is the frequency that is calibrated from the satellites, which is super accurate, and use that to calibrate it. And so this frequency counter should be within a hertz or less of accuracy here at this frequency. We get what? Went below 700. Yeah. Well, we'll have to. I'm gonna use 112.7 kilohertz here. I think that's a good number. And really, the only reason we're using a number is, remember, if we need to measure the ESR for low capacitances, and even then, it's not super critical. I use this frequency counter just to have at least an idea of what it is. But we need to subtract the capacitive reactance for low value capacitors, about 22, 33 micros or lower, so that we have an accurate reading of the ESR. Okay, so maybe I'll do 1126. I think that's good. It will work its way down to that, so we'll use that. So we're ready to do the ESR measurements. I modified the circuit here to include that 32.5 ohm resistor in series with the output. And so looking at the schematic, I basically added that 33 ohm resistor right here in series with this 2200 microfarad capacitor. So what that means is that our RS here in the formula is going to be that 38.2689 ohms. So plug that in there. The source voltage is, we measure that with no load. And that we measured, I think, before to be 607 millivolts, but that changes a little bit, so we'll measure it, right as we do the ESR measurement. And then this one's the voltage measured across the capacitor when the capacitor is in the circuit. So that's sort of the quote-unquote raw ESR. And then to get the real ESR, we want to subtract the reactance of the capacitance. So the reactance is going to be this formula here, which is 1 over 2 pi FC. So at 112 and 0.6 kilohertz, I think I put that in there. We can actually calculate that reactance and subtract it from the ESR. Anyway, all this stuff I can do on paper, but everything I put into an Excel spreadsheet on my phone. So we're gonna go through each capacitor and plug into the spreadsheet and see what it measures. Okay, here's an example capacitor. It's right over here. It's hooked up to the scope. I don't have the scope screen here, but it's reading about 38 millivolts. So it is pretty good. So we went down from 0.69 volts, so 690 millivolts, to 38 millivolts. I plugged that in here in this little Excel spreadsheet, and you can see it pretty clearly here. And then we get an ESR of 2.25 ohms, which is not great, but it's not bad, right? So, but I wouldn't use this call this as a high quality capacitor. It's pretty good. It's a good capacitor, right? So it wouldn't be I wouldn't throw it out, but I would put it in the sort of mediocre ESR bin. So here's another capacitor. It's a little 2.2 microfarad capacitor here hooked up. The scope is measuring 58 millivolts and at 2.2 microfarads. We do have a little bit of reactance at this frequency, which is 0.64 ohms. So I've already subtracted that. This spreadsheet subtracts that from the ESR, but the ESR is higher in this one. So this one is 4.15 ohm ESR. I would call this is not a good capacitor, even if it's just a small one. Not going to be used for really rectification or anything like that, but 4.15 ohm ESR is pretty high. So I would throw this in a low quality bin as far as ESR goes. So the previous capacitor was maybe in a medium quality bin, but this would be a lower quality. Still a good capacitor. Wouldn't necessarily throw it out, although I did just replace these from a receiver, so I'm throwing it out because I'm just picky about capacitors, but it's still a working capacitor. Okay, here's a 100 microfarad brand new capacitor. So I put 100 here. I'm measuring 35 millivolts on the scope, and the ESR is 2.05, and of course the reactance is very, very low, 0.01 ohm. So this one's a pretty good capacitor. In fact, this is one of the capacitors I'm using to build a circuit. You might be asking, like, wait a minute, the capacitors in the circuit have some ESR. Does that affect things? Do you need to get like a really super low ESR for the circuit? It really doesn't matter actually, because remember what we've done is we measured the internal output impedance, or RS, of the oscillator. So if you really have some crappy capacitors, you'll just get a higher impedance, which is okay. Not ideal, but it's okay. It's not the end of the world. In fact, we had to increase the internal impedance, output impedance, by putting a resistor in series. So that's equivalent to having some less than ideal ESR capacitors in the circuit. So it really doesn't matter as long as it's measured, and then you can know those numbers, right? So that's the trick with this circuit, is that it doesn't have to be this super low ESR circuit. It really it's not a point. It's not something you need to do. So here's a capacitor that I know it's bad. It has really bad ESR. I took it out of an old radio, and you know, the sound wasn't good. It was really quiet. So, and I know this was the faulty capacitor, and so just as a test, you know, always like to test this as a reference point, right? And you know, lo and behold, the measured voltage barely dropped. So it's, you know, it was 690 millivolts to begin with no load, and then with the capacitor across it, it's 680 or so. And this is a 1 microfarad capacitor, so it has, you know, fairly high reactance, but that doesn't really matter because the ESR comes out to be, you know, 2.6K kilo ohms, which is insanely high. So this is an easy way to tell that this is a bad capacitor. Now, this capacitor does not necessarily register as an open, because it does have a little bit of, you know, juice in it and some ESR, so you will get some signal through it if you have a high impedance source. So if you have a amplifier, like a preamplifier, this capacitor might let some signal through, and it did. You know, I did hear audio through it, but you know, it's really bad. Like a 2.6 kilo ohms, definitely this is a throwaway capacitor, and the only reason I'm keeping it is to test these sorts of circuits. So there you have it. That's all the capacitors I have, sort of in the variety of good to bad. Well, we reached the end of this video, and thanks for watching the build of this ESR capacitor tester, and hopefully you will take on, you know, building this on your own as well. And do let me know in the comments if you have thoughts or questions or suggestions. I'd be happy to answer them and discuss further. And this is an interesting circuit, an interesting way to measure ESR. And there's many other ways, many fancier ways to do this. I just chose a simple and inexpensive approach where, you know, you have common parts and build a simple circuit to make this measurement device. Well, thank you for watching, and I'll see you next time.